Hi everyone. Today we're going over Grignard reagents. So off to the right is Victor Grignard, and these reagents are named after him. So Victor Grignard was a French chemist. Oops. And he won the Nobel Prize in Chemistry in 1912 for his work in organometallic chemistry. Now, he sounds pretty great, but he also helped develop a chemical weapon called phosgene in World War I. So unfortunately, back then, a lot of chemists were asked to help develop um, chemical weapons, uh, either in World War I or World War II, and a lot of them went on to regret doing that. Let's talk about Grignard reagents. So Grignard reagents can be used to make carbon-carbon bonds. And we're going to see another benefit of a Grignard reagent on the next slide when we go over an example problem. But for now, let's just kind of go over a general mechanism for Grignard reagents. So what you want to do here is start with an alkyl halide. So the X here is a halogen, and you could either use bromine, chlorine, or iodine. Now normally we say that you can't use iodine because it's too slow, but in this case you can because we're just using an alkyl halide here. Now we're going to add in pure magnesium metal. So I'm putting a little degree or not symbol next to that to indicate that it's pure. And then we're going to dissolve all of this in an ether. Now what you end up getting is kind of strange. So that magnesium kind of wedges itself in between the halogen and the carbon that the halogen was bonded to. Now, remember, if we think about electronegativity values, metals are not electronegative. They have very, very, very tiny electronegativity values. So here, carbon is actually going to pull electrons towards itself because it's more electronegative than magnesium. So let's just make a little note. Carbon is more electronegative than magnesium. So this actually does have some ionic character. So we could also draw this as carbon having a negative charge and magnesium having a positive charge. Now, because we have that distribution of electrons towards carbon, we can now react that negative carbon with something that's partially positive or fully positive. So let's say we have a ketone, and we'll just draw acetone here, and we react this with our Grignard reagent. So again, the carbon is partially negatively charged, and the magnesium is partially positively charged. So that partial negative carbon can attack the partial positive carbon on our ketone. Now, when it attacks that carbon, we then see a movement of pi electrons up to oxygen. So again, we're creating a carbon-carbon bond. So let's draw this in a little more detail on the next slide. So I'm just going to redraw our ketone, acetone, and our Grignard reagent. This time I'm just going to put an ethyl group on there. And let's use bromine as our halogen. So we would call this ethyl magnesium bromide. And again, this is our Grignard reagent. But the Grignard reagent can come in many different forms depending on the carbon chain that you want to add to your other starting material. All right, so let's see what would happen here. So again, we've got our partial negative carbon, and then our partial positive carbon is on the ketone. So the partial negative carbon is going to come in and attack that partial positive carbon, and then electrons will move up to oxygen. Okay, so we have two methyl groups that were originally bonded to the oxygen, the carbon that's bonded to oxygen. And now we're adding in an ethyl group. So let's just highlight what we did here. So we added that 2-carbon chain to the carbonyl carbon. We also moved some electrons up to oxygen, so now it is negatively charged. And that can be balanced by the magnesium bromide that's left over. So in the last step here, we probably want to protonate that oxygen. So we can just use a weak acid like water. So that will, oh, I went a little crazy with my arrow. All right, so that would come in and take a hydrogen, and then we'd have our final alcohol. And what type of alcohol is this? Is it a primary, secondary, or tertiary alcohol? A tertiary alcohol, because the carbon that the alcohol group is bonded to is tertiary. Now, previously, we said that you can't make tertiary alcohols, but that was when we were using carboxylic acids and aldehydes and ketones and esters. So those 4 types of functional groups cannot be reduced to a tertiary alcohol. They can only form primary or secondary alcohols. However, here we're not doing a reduction, we're using a Grignard reagent. So this is an entirely different reaction that allows us to form a tertiary alcohol. So I'm going to write, yay, we can form these. So if you ever need to form a tertiary alcohol, just use a Grignard reagent. Okay, so let's do another example. So we've got our ketone here, and there's a ring structure. So let's see what that does. Let's say our Grignard reagent is a benzene ring bonded to magnesium bromide. And then in the second step, we'll add water to protonate our oxygen. So what I would like you to do is pause the video and try to figure out the product on your own. And I would also like you to draw the mechanism for this reaction. So draw the arrow pushing mechanism. And then when you unpause the video, we'll go over it together. All right, so let's draw the mechanism because that will help us determine the product. All right, so again, in our Grignard reagent, the carbon next to magnesium is partially negative. Magnesium is partially positive. And then the ketone carbonyl carbon is partially positive. I'll use blue for my arrows. So the negative carbon is going to come in and attack the partially positive carbon on the ketone, and electrons are going to move up to oxygen. Now this is where things get a little complex. All right, so we just formed a bond between the carbonyl carbon and our benzene ring. Okay, so our new bond is the one between the two rings. And again, in the last step, we're going to protonate the oxygen. Oh, let's see. I'll just draw my arrow all the way around. There we go. And now we have our final product. So again, what type of alcohol do we have? A tertiary alcohol. And also, let's think about stereochemistry. Do we have any stereocenters in this molecule? Well, it kind of looks like the carbon that the alcohol is bonded to could be a stereocenter, but if we go around this ring here, it's equal on both sides. So that wouldn't, or that would technically count as two of the same group. So we don't have any stereocenters. So we only have one product. We don't have enantiomers, for instance. But maybe that would be different if we had a different starting material. Now, instead of a ketone, what if we start with an aldehyde? So let's look at an aldehyde. And let's use a Grignard reagent where we just have a CH3 or methyl group bonded to magnesium bromide. And then we'll follow that with water. What would the product look like? And feel free to pause the video and try this on your own first. And also drawing the mechanism can help to figure out what your products are. And then when you unpause, we'll go over it together. Okay, so again, we have our partial negative carbon, partial positive carbon. So let's redraw those and we'll show what happens. Okay, so the negative carbon comes in and attacks the partial positive carbon in the aldehyde, and then electrons are moved up to oxygen. Okay, so our oxygen now is negatively charged. And then we also added a carbon. So let me actually count carbons here. 1, 2, 3, 4. And then the methyl carbon is going to be our fifth carbon. So 1, 2, 3, 4. I need one more carbon. 5. Okay. And again, in the last step, we're just going to protonate the oxygen to get our final alcohol. And what type of alcohol do we have? A primary, secondary, or tertiary alcohol? A secondary alcohol. Now, one other thing we should consider is, are there any stereocenters? Yes, there is a stereocenter where the alcohol is attached. So remember, there is a hydrogen back there too. So that carbon is bonded to 4 different substituents. So we could have a situation where the OH group is in a wedge or in a dash. And what is the relationship between those two? They're enantiomers, and they'll be present in a 50-50 mixture. So we have a racemic mixture. All right. Now let's do another example. And actually, I think I mislabeled the last one as a challenge problem. This one's actually the challenge problem. I think I flipped my slides a little here. Okay, so in this problem, let's try the following. What if we start with an ester and we add our methyl magnesium bromide again, followed by water? What would happen? So I encourage you to try this on your own first. So you can pause the video, go through the mechanism, and then when you unpause, we'll go over it together. All right, so let's redraw our starting materials. So just like last time, the partial negative carbon will attack the partial positive carbon on the ester, and electrons will move up to oxygen. So oxygen becomes negatively charged, and we've added a methyl group onto that carbon. And I'll actually highlight that methyl group. Okay, now what would happen next? So you might think that we would protonate the oxygen, right? But recall from our previous discussion of esters that we do have a good leaving group on our ester. So the oxygen could use one of its lone pairs to create a double bond and cause the leaving group to leave. So now we have acetone as one of our intermediates, as well as an alkoxide. And this is actually called the methoxide ion because we have a methyl group on a negatively charged oxygen. Okay, so what would happen next? Any ideas? Well, we presumably do have more Grignard reagent, especially if we add excess Grignard reagent. So let's say we've got another methyl magnesium bromide hanging out. The negative carbon, again, could attack the positive carbon on our ketone, the acetone. And now we're kind of doing the same thing that we did before. So this time, we're adding a third methyl group onto that carbonyl carbon. And now we can finally protonate and get our alcohol product. All right, so this is again a tertiary alcohol. So if you start with an ester, remember esters have a good leaving group on the end that can become an alkoxide ion. So you actually end up going through two steps here with those Grignard reagents. In the first step, you add an alkyl group and then cause the leaving group to leave. In the second step, you add another alkyl group and then you protonate to get your alcohol. All right, so I think we'll stop there today with Grignard reagents. Next time, we're going to talk about protecting groups, and then we'll also start to review how we can use alcohols to create other molecules. So we'll kind of go in the opposite direction from preparation of alcohols. So I will see you then.